Alright guys, so today we're going to be solving some linked list problems. I don't want to go through a few of them together with you guys. I have them kind of in order of like what I think would be good to understand. Um, yeah. I think we're going to have to put this one. Let's put this here. So let's start off with one of the basic linked list problems, probably one of the first ones that you'll get exposed to, which is the middle of a linked list. So basically the problem just reads that given the head of a linked list, a singly linked list, return the middle node of the linked list. There are two middle nodes, you return the second middle node. With this problem, we can see that the example from LeetCode, we have 5 nodes, and the middle of it is obviously going to be 3, right? 2 on the left, 2 on the right, the middle one is 3. Now, the second test case that they gave us is when there's 2 middle nodes, meaning that the list is of even numbered elements. We have 6 elements here, 6 nodes. And of course, they want us to return the second middle node. So in this case, instead of returning 3, we return 4. Right? And the output isn't going to be simply the node. You're going to return the head starting from that middle node, right? Because here, the head of this output is 3, which is the middle node, and then we still return 4 or 5. Okay? For this one, head of this middle node, well, like because of the middle node, the head now becomes 4. So we return 4, 5, 6. Okay. So one of the ways that you can solve this is you can, at least for me, when I first saw this problem, I said, well, I can just count the number of elements, right? I have an odd number of elements. I know I'm just going to get the middle of that. So in this case, we have 5, right? We know that we're going to want to get, we're going to count up until the middle element, and then that will make that middle element our head, and return it. However, that would take O of n squared time, just because we're counting at the worst case, right? We're going to be counting the whole list. And then when we find the number of elements, we do some computation, some logic. And then by doing the logic, we'll get the middle element, like the position of where the middle element's at. And then again, we have to traverse through the linked list again, starting from the head at 1, 2, and then 3. We say, okay, now here's our middle, and return the rest. However, there's a nice little technique with that's called, using fast and slow pointers. You also might have heard it as the tortoise and hare solution. And the way this works is that we will have 2 pointers, and we're going to move 1 pointer slightly faster than the first pointer, right? So if I do some work here, so if I have 1, 2, let's tab these out. Say I have this, right? We're going to have 2 pointers, S and F, right? Slow and fast. They're both going to start at 1. Now, say I move the slow pointer 1 position at a time, and I move the fast pointer 1 position faster than the slow. So you can think of it twice as fast, right? So when slow moves by 1, when slow moves to 2, I'll put this in the new line. Slow would be here. Fast would be at 3. In the next iteration, I'm going to have slow move to 3, then fast will move to 5, right? Because it's jumping 1 extra position, right? Notice how slow moves once, fast moves twice. Slow here moves to 3 once, and then fast moves twice to 5, right? And notice with this case, what happens when our fast pointer reaches the end of the list, right? Where its next pointer becomes none, we know that it's at the end of the list, right? If f.next is none at the end of the list, our slow pointer points to the middle. We can try this same method with the second test case that it gave us, right? So for this test case, right, we're in this position. I mean, all the iterations will be the same up to here. Now, we move slow once, and fast would be twice, right? So here, fast is at none, but fast.next, it won't be anything, right? So our loop would break out here, and we just return slow, right? So there's to think about is the time complexity of this. This would be O of n time, because we're only going to be traversing the list 1 time. Every time we're going to be traversing it only once. And in terms of space complexity, this is actually constant space because we're not manipulating the list. We're not going to create a new list. So we're not going to have to create that, like find that additional memory in space. We're only going to be using two variables, which would be our slow and our fast pointers, which will help us keep track of where we're at in the list. Okay. There's one test case that they didn't show here, and I think this is a test case that you should always bring up to your interviewer whenever you're given like an array problem, a string problem, like any problem in general. You always want to find like one of like the very, very simple test cases is like, what would happen if we get an empty input? So in this case, if head is empty, like if there's no linked list, like it's just like an empty linked list, what do we return, right? In this case, we see that in most cases, the easiest way to do it is look at the data type, the type of data that you're returning. And here we want to return a linked list, right? So if our input is empty and it doesn't specify in the description to output -1 or something special, you can, in most cases, return back an empty list or an empty array, right? Or if this is a return type of a Boolean, then of course we would return false. Okay, so that would be the first base case. Let me delete these. I'll do that at the end. So here's the base case, right? Or like the empty case, I'll call it. If head is none, right, we return none. Make sense? If there is nothing in the head, we're just going to return none. That means that there is no middle element. Okay? We don't return the empty list here because the middle of an empty list is not the empty list. The middle of an empty list is just none. Now let's set our pointers. We're going to have slow and fast pointers both be head, right? They're both going to start at head. So we can say slow equals head, fast equals head. However, you can also write this as something different. You can say slow equals fast, which then equals head. Okay. Now, what loop we're going to use? Obviously, in most linked list problems, you're going to use a while loop. So while, two conditions, right? One of the conditions that we know is we're mainly checking the fast, right? We're checking the fast pointer at their every iteration because the fast one is the one that's going to reach the end of the list first. So while fast is what? Well, first, while fast is true, right? So while fast, and what else has to be true? Fast.next has to also be true. You know what I mean? Why? Because then this will help us tell when we're at the end of the list, right? Here, fast is true, but fast.next will not be true here. Even though this pointer, essentially right here, is none, like this element here, right? The end of the list is none, the tail. Fast.next, remember, fast.next is going to be fast.next.next, right? A little bit of a hint for what's going to be in the logical while loop. Why is that? Well, it's because we're moving the fast pointer twice. We're not moving it once. So fast.next is essentially two steps, right? So in this case, fast.next.next is going to be none. You know what I mean? So therefore, this will break out. Okay. So what is slow going to do? We're going to move slow pointer once. Cool. And then fast, we're going to move that twice. Okay. That's done. And we know that once we're done at the end of this while loop, once one of these conditions break, when one of these are false, we know that our slow pointer will be middle of the list. And why don't we have to just, why can't we just return slow, right? Well, because slow is our head. And we're going to be manipulating this while also maintaining our original head from the input, okay? And that's it for this problem. Very simple problem, okay? We can also see that if we do the test case of an empty list, oh, it's expected to have a size 1. Okay, I didn't even see that. Where is that at? Right here. The range of 1. Okay, so I guess we really don't need that first test case, but it's always good practice to have it. Cool. This is done. Let's submit this. I've done this problem multiple times. Hope you guys stick around for the next video. That would be talking about a linked list cycle.